Welcome, everyone. This is Linda Westphal from the Software Excellence Academy, powered by the Westphal team. And I'm delighted to invite Tom Gill back. He's our #1 webinar presenter here. He gets more attendance than anyone else. And he's going to be talking about Agile engineering today. Basically, not just doing Agile, but doing Agile from an engineering perspective, and adding actual engineering principles and practices into our Agile projects. With that, I'm going to turn the presentation over to Tom so he can have as much time as possible to actually talk to you today.
Okay, everybody, welcome. Thrilled to have you there. I hope we have a few extremely interested people who want to turn these powerful ideas into interesting change at their places of work or in their company. And anybody who wants to do that, I will support you in any way I can, starting with an awful lot of offers of free written material. So you might like to photograph the first screen because that gives you URLs to these slides. And many of these slides contain a lot of detailed URLs you might want to capture. I also have a QR for my Agile library. It's just about everything I've written about Agile is in there. So enjoy that. I will be showing you these QRs later, and of course you'll get a copy of the slides, and you have a video of this will probably be out in about a week. If all else fails, write me an email saying, please send me your slides or at least the QRs. Okay, so Agile engineering. I believe that the best way to do Agile in a large and complex environment, as opposed to a trivially small environment, is the way any large projects like skyscrapers or national health systems are done, and that's using an engineering approach. And what do I mean by engineering? Well, we're going to look at that, but it means systematic, quantitative, logical, fact-based, and that kind of stuff, okay? Here's an overview of what I'm going to try to cover, about a little over 17 slides, actually about 30, about 1 minute each. And each slide is packed with stuff that I could probably happily talk about for an hour. So it's going to be very condensed. If something turns you on, you're going to want to go back to it, pick up the free links, study it, maybe talk with me about it. So this is not a systematically teaching you in slow motion simple ideas lecture. I'm going to give you an overview of what it means to be engineering and doing Agile. And up to you to say, I want to learn more about that. And then I'm going to give you lots and lots to read. And if you're serious, I'm going to give you free access to me to talk about it and maybe develop your own books or lectures or courses or consultancy or in-house change. So I've been doing this a long time. So here you have my software metrics book, came out in United States, 1977. And here's a software metrics. So I'm definitely quantifying software things from a fairly early stage. And here's my competitive engineering book. You can get a free digital copy of that. You'll find that floating around here. And I'd like to quote to you what I said, because I'm quite proud of it. By the way, I started working for IBM in 1958. So by the time I published the software metrics book, I've got about, shall we say, 18 years of practical experience as a consultant on the public market. And I've been doing Agile since about 1960. Okay, that is, I delivered real systems in small increments of value to users. I didn't have a name for it. We sure didn't call it Agile. I later called it EVO, Evolutionary Value Delivery. But it was, looking back, it was just Agile. And I used my common sense to arrive at the idea that I should do things in small increments and see how well they worked before adding more increments. So here's the quote from the book. And the European edition was 1976, if you want to date this historically. A complex system. Now, So if you have a trivial system, one man can can do it in a week. We don't need engineering, and you can just code it and you're all done. So I'm talking about large and complex systems, okay? Non-trivial systems, systems that people tend to get wrong, run over budget, have terrible problems with, those systems. A complex system will be most successful if it is implemented in small steps. And mind you, this was Big Bang waterfall era, okay? And if each step has a clear measure of successful achievement. So in other words, success is quantified and we're measuring that we're moving towards that success incrementally. We're not measuring that we're delivering more code. If the primary reason for our project was better security, we're measuring security, the major point. And as well as a retreat possibility to a previous successful step upon failure. So a ambitious step can fail, and you need to quickly go back to what worked rather than saying the entire project will take another 4 years to deliver, okay? So I'm quite proud of that, but I'm still busy selling the idea to the IT community, because this is not most people's definition of Agile, but it's my definition of Agile as it should be. Okay, number one of about 17 different things here. What is real software engineering and systems engineering? Okay, and I took some advice from this fellow here. I just got an email from him today. He's very much alive and well, and in Austin, Texas, Professor Emeritus Billy Cohen, and he's devoted his life to figuring out one thing. He's a professor of mechanical engineering. What is engineering? Okay, we use the term all the time. Lots of people have degrees in it and certifications and say they do it. But Billy sat down and said, I'm a professor of engineering, and I have a feeling like not everybody agrees what engineering is. So he started decades ago. He finally wrote a wonderful book called Discussion of the Method. I just had a copy of it in my hands today in my library. If you want to go really deep, if you're a really deep thinker, get the book. Otherwise, there are some papers and videos in the link here. But now I'm paraphrasing Billy's definition in my own glossary of 700 terms called Planguage Glossary. And you get, if you want to know how I define stuff, you'll find it here in this link, Planguage Full Glossary. Anyway, paraphrasing, pretty close, but using my own terminology and ideas. Engineering is an evolutionary process using practical principles. Notice it says principles of software engineering management here. And there are 144 of them, somebody counted. In order to determine and identify the means to deliver. Synonyms for means to deliver are design, architecture, strategies. That's the stuff we deliver to get better at our values, our stakeholder values, our qualities, our objectives. And it means to deliver the best achievable performance. Now, in systems engineering, performance includes all qualities like usability, technical debt, things like that, security, and cost levels. And then it's got this word balance, and I love the word balance. You can't maximize, you can't just optimize one quality. I saw something recently, got to maximize the security. I said, no, because that would steal all the budget and steal qualities from it. You have to make do with sufficient security, okay? But you can't just maximize it at any cost. For optimal stakeholder satisfaction, that means satisfaction of a mix of stakeholders, okay? And optimal means pretty good balance. Nobody's got anything maximized. Costs are not zero, but there's pretty good balance in a complex, risk-filled environment. Okay, you might like to read that in slow motion later, but that's my definition of engineering. That's a Texas definition of it, Billy, and sticking to it. Okay. Now, second point, we're software people, And for a lot of people, that just simply means programming and coding and little else. I always thought that was strange because I always thought data was pretty important. In the old days, we used to call it data processing, okay? And data is not hard, it's soft. So why people systematically eliminate or specialize in data and only think of programming always struck me as strange. There's a very intimate relationship between the logicware and the dataware. But then there's people in the loop too. And we can't forget people and their motivation and culture and everything else. And oh, by the way, you can't run the logicware and dataware and interface with people without hardware, okay? Which includes all kinds of stuff like netware or cloudware, if you like. I at one point in one of my books, I called programmers soft crafters to distinguish them from software engineers. Okay, so and a lot of people say, I'm a software engineer, but they really are a craftsperson. And I hope they're a really good craftsperson, and they need to be. But craft is not engineering. Craft is just doing what is traditional, it works. Engineering may be thinking outside the box and like, is it legal according to regulations for privacy or security? Does it correspond to larger scale plans in your corporation? Does it mesh with the culture? So I'll make a long story short. I believe that software people have to be systems people, not just coding people, whether they like it or not. And if they choose to say, I specialize in coding and software and I don't care about all the other stuff, that's okay. You're a soft crafter, okay? But you cannot make your system successful for your corporation. Somebody else, a real systems engineer, a real enterprise architect is going to have to do the job of considering, all these other things, okay? So let's see, I've got the control panel here, okay. Now, point number 3, stakeholder engineering. We have a culture which is very proud of itself, that it considers the users and the customers. Okay, that's what you'll find in like Agile Manifesto things. Now, that's good, much better than just considering what the programmer wants to do, considering other people. But in large scale systems, there's much more to it than the customer and the user. There is a class of things that systems engineers call stakeholders. I know most of you know the term. But it turns out if you, in a large complex system, start listing all your critical stakeholders, meaning those you really have to listen to, otherwise you will risk failure, you will find that you have 20 to 40 different stakeholders. And most of those are not users and they're not customers, but they might be the law in Europe, which will fine you $1 billion or prohibit you marketing their product. And they're pretty powerful. So you have to say, what are their requirements? I have to build them in. I finally did what I've been threatening to do for a long time. And in 2021, I wrote a book called Stakeholder Engineering. There's the QR to your free copy if you want to go into depth. But this is part of engineering, is doing serious stakeholder engineering up front. Stakeholders, in short, are the source of our requirements, right? And a lot of them don't have user stories. They have constraints, like you must follow the law, okay, and things like that. So long story short, get the book if you want to upgrade your skills in the stakeholder area to the engineering level. Here's an enlarged view, so you can almost read the text on the many stakeholders in a particular application. And these stakeholders are stakeholders because they have some values. That's the little yellow arrows here, your qualities and values. And stakeholder is a stakeholder because they have some opinion about some of these values, some of these quality requirements, if you want to call them that. And we have to listen to what they want and need. And 5 different stakeholders may have 5 different opinions about the accessibility of the system. And we have to somehow reconcile that in our software engineering or systems engineering. Okay, so enough of that. 0.4 out of 17. And I'll take a little peek at my watch where we'll survive. Now, the fourth idea is that we are dealing with multiple stakeholder values simultaneously, okay? I often say that you can easily make a list of 10 or 20 or 30 things, values that you have, but if you ask a simple question, what are my top 10? Sometimes it's a good idea to prioritize or focus on your top 10 values and say we'll note the other values, but we'll do them when we have succeeded in doing the most critical 10. That's the prioritization idea, and it makes complex systems a little bit simpler. You're not ignoring all 30 of the critical ideas, but you're deciding I'm going to do the top 10 first and master that and see if I have enough resources to deal with lower priority values. So typically you have to deal with 10 simultaneous things. This is like security and user friendliness and adaptability to the market and transparency and on and on and on like that, okay? But what are your top 10? And by the way, in my world, all of them are stated quantitatively and they can be measured in practice as you iterate, okay? So that's pretty complex. It's like trying to juggle 10 balls in the air simultaneously and not drop any one of them. Anybody can throw a ball up and down with one hand, one ball with one hand, but try it with 10 and you're a pretty good juggler. And you need tools to juggle 10 values simultaneously. And not only that, we also do multiple cost ideas. Many people either don't do cost at all, they just hope they won't run over their budget or deadline. But when they do it, they maybe focus on the capital cost. But that's why we get problems like technical debt, which far exceed the capital costs. And we need to consider all the time, people, money costs for the life cycle of the entire system. We need to consider that when doing our design, our strategic planning, our architecture. And we need a tool, because now I'm saying in practice, you're going to have to look at 10 values requirements and 5 or 10 cost constraints or requirements. When you look at any design or architecture, you're going to have to match that. You're going to need tools to do it. By the way, if you bring in a set of designs or an architecture and say, how good is that for my top 10 values? That's what I call the effectiveness measure. And if you look at the cost of those designs for your in all phases and all types of costs, you get your cost requirements. You can actually compute the values over the costs, values here and balance symbol over the cost, and you get what I call architectural efficiency. In other words, and that's what most of us, this is also what I call balance, okay? So we have to get a reasonable balance, with a reasonable satisfaction of stakeholder values at reasonable set of costs. And that's all we can ask for, is being reasonable, and maximizing towards infinity is just silly and going to get you into trouble. 0.5. I'm going to take a little time here. On the right-hand side, you have what I call an impact estimation table. And most of the books I have given you the links to, and giving you more here, they talk about how to do this table. It's pretty simple. I'd like to at least give you the idea that you can do this, but it takes me one day in a workshop on a course to train people to do it. So I'm not going to try that here. But let's look at the structure of the table. On the top level, we have 1, 2, 3, 4 different, let's call them designs or solutions or architectures or strategies. Those are just synonyms for stuff we're going to build, acquire, and put in the system so that we get some values delivered. So on the left-hand side, where it says requirements, we have yellow value arrows again, and we have names like, let's see, collect information, education, get people where they need to be, healthy employees, stay healthy. This is actually COVID planning values. It says there, So the question is, to what degree are we satisfying these values? I mean, ideally, if this right-hand number is our goal for all of these, how good we want to be at a certain deadline, then we'd like a set of designs. If this is the entire set, we'd like the entire set to get us to our goal. That would be a perfect design, okay? If what we're doing here with these little bar charts is we're saying, okay, this health architecture, how much does it move us in our collect information value from present status of 50 to the level we want to get to 90 on some defined scale of measure? And the answer is a disappointing 13% of the way, from 5 to 55, okay? Well, not a total failure, but nothing to write home about. Now, but so what is this transport architecture? Well, there's a light bulb symbol, and it means a design, a bright idea. And the estimate is it gets us 50% of the way to our goal. Hurrah! That's not bad. 1 out of 4 gets us halfway. Why, we've practically solved our problem. And what about this Tuda architecture? That gets us 63% of the way. Hey, maybe this plus this is 100%. Maybe the two of these alone get us to our goal. Wow, number 4 even gives us 75%. Maybe we don't need that because we've got this and that. Maybe we don't need that either. Okay, so what we're doing is we're evaluating the effectiveness based on history and knowledge of these in our past projects and other people's projects, or by admitting we're just making a scientific wild-ass guess, swag. And we're using this information to say, will one of these do everything we need? Okay, if all of these had been at 100%, that would have been the truth. This one's pretty weak. It's weak, and a question mark means nobody's even evaluated. We have no idea how good it is for these. It could, these could even be negative and bad, negative side effect, weak. So this is pretty much of a loser. But at the same time, we also say, wait a minute, how much is, this looks very powerful, but how much is it going to cost? And the answer is 1% of our days to implement budget. In other words, we can do it quickly. And it says here 10% of our capital cost budget. We can afford that. This is pretty good. The value to cost ratio is pretty good here. It turns out the values to cost ratio of the transport architecture is marked in green here. It's simply been computed that it gives the highest efficiency, the highest value to cost. So this is maybe something we could deliver as an early sprint or set of sprints to get the most value at the lowest cost. Here's another way of, you can do this on any spreadsheet, of course, and here you can, using a spreadsheet information, you can generate a little bar chart. Here we can see that this transport architecture one has really good value and really low costs, okay? Whereas this has low value and almost the same cost, so that's sort of a loser. Anyway, this is what I mean by multi-value optimization, multi-constraint, thus the cost under consideration. And this, I'm trying to introduce the idea, this is engineering. I don't just talk about these things and say this is really cool and lots of people have done it and Google has used it, therefore it must be good. That's all childish activity. We need to say, how much will it give us on our quantified goal? And by the way, we ask questions like, do you have the evidence and will you write it down for why it gives 50%? Pretty shocking idea, huh? But this one table alone is my picture of, this is what I mean by agile engineering. We now have already decomposed into 4 different possible sprints, and we could also say this is also a decomposition. We could focus on a sprint on just one value and or one of these. So we're already beginning a sprint type decomposition. Point number 6. Keep an eye on the watch. Not doing too bad. Okay. You meet Mr. Quinnen, who worked at IBM Federal Systems Division, building software for space and defense projects at IBM. And Quinnen is the architect, the designer. And they reported that they developed a thing called the Cleanroom method. You'll find detail down here in this source, Quinnen. And they claimed that they managed to move from their projects being late and over budget and losing money and bad quality to always being on time, always being under budget, and always delivering state-of-the-art military and space quality levels as required by the contract, like 99.98% availability for a flight system. And then the question is, how did they do that? Because you don't know how to do that now. Okay, if I'm wrong, please write to me and tell me how you accomplish on time, under budget, highest quality, complex space and military systems every time, because I haven't met anybody else who does this. And the answer is they were using a form of Agile, but they're using my kind of Agile, and they measure their progress at every step, which is what we call sprints. And they're asking, am I moving towards my 99.98% availability goal as expected, like 0.2% sprint? And if the answer is no, we did not move, but we thought we would, they call in their architect, Mr. Quinnen, and say, Quinnen, do something. What? Redesign, re-architect, come up with something that gives more effect at less cost. And we'll try it out on the next step. And if we have a winner, we'll do it many steps until we're at 99.98. In other words, here's a fantastically interesting idea, which has been massively tried out in practice, which nobody seems to teach at universities or put in their books about software engineering. Yet it's one of the most powerful software engineering ideas I've ever seen. IBM used it only internally. They didn't sell it externally. They didn't want their competitors in the space military to know about it, frankly. Okay, so that's one reason why nobody knows about it. But it was published in the IBM Systems Journal, as you can see down here. And okay, but here's the basic idea. We can use Agile step by step to get numeric feedback on the real cost of the step and the real numeric value. And if the cost is too high or the value is too low, we will redesign right then and there, that week, that month, and try to improve our architecture or design so that it is more effective and less costly. And then we'll try out our architect's new theory, see if it works in practice measurably. That is a fantastic idea, and everybody should know about it. And that should be part of, I call it Agile as it should be. Okay. By the way, this is identical with the quotations from my software metrics book I gave you on slide 3 in 1976. By the way, I didn't just read about this. I worked with these people for several years personally. Point 7. Now, one of my favorite customers is called Intel. This is a large engineering firm. I mean, almost everybody they hire has a degree in engineering, but a lot of them are doing software, and not even their hardware chips are effectively programs, software. 2 decades ago, they started using most of my methods, training people on 2-day courses on them. And by mid-2016, 13, they had trained 20,000 Intel engineers in my planning language and my quality control methods and my EVO methods. And they're starting to do in-house research on how it works. Here's the guy doing the research. You can get his paper. Here's one thing they did. They used my planning language to quantify their requirements and make them clear. Okay. Then they have a quality level. They have to have almost perfect quality requirements, because when they don't want their requirements to get hardened into a chip spread in the millions around the world and discover they have a bug. They're not like Apple that can go in and change their software with a weekly update. They're hardwired. So they have a criteria that their logic has to be incredibly high level. And so here's an example using my defect prevention and specification quality control process described in, for example, the competitive engineering book. and they submit 31-page requirements, and they find 312 defects. These are violations of their rules. Like, one rule is the spec must be perfectly ambiguous and clear, no way to misunderstand it. Okay, and so that's 10 defects per page, and it turns out their standard that is profitable for them to release their requirements to is 50 times better than that, 0.2. So what they say is no exit for your requirements, go back and try to follow the rules. And the team keeps on doing that. It might take them weeks or months, but finally they deliver 45 pages of the same requirements, but much better written. They find only 10 defects, meaning 0.2, and they say, well, it's not perfect, but we cannot continue until it's perfect, or we will never deliver any chips. So we're going to have to hope that we will discover the few remaining flaws in the other processes, but it's important there are very, very, very few defects. So we will release your things there. By the way, this level is about 10 times better than you probably have today with your requirements methods. The Planguage, or planning language, being quantified and structured, gives about 5 to 10 times better quality of intelligibility. And so they start off at a pretty good level, and they're trained for 2 days in the methods, but they're human and they screw about and they're under time pressure. And so they use this quality control process known as Spec QC to motivate the team to go back and do their job 50 times better before they're allowed to release their requirements. This is engineering by an engineering company that has kept using my methods for 20 years because they don't know of better methods yet, to my knowledge. Okay, and I do know. Okay, so another example of real engineering. Okay, keeping an eye on the time, probably go a little bit faster, but okay. Now, this slide is using the same method, the impact estimation table that I was showing you earlier. It's the same table. And the point, I've already sort of made it, so maybe I can save a lot of time by not telling too much about it. But notice that it did a computation. The set of these, which is equal to this number, values, hopefully estimated as being deliverable, over the set of these, which is the cost estimated, gives 40.70. Now, we've done a similar calculation for this design, this design, this design, and this design. All of these designs might be sprints or increments. You can think about them that way. But they might be so large as they have to be decomposed into smaller increments. That's another matter. But we let our spreadsheet compute the values to cost ratio. You can almost see it graphically. A lot of values, little cost. This must be good. But you know, this is 40.70. This is only 12. This is 39. This is 21. What it's doing, it's computing the priority. You know the joke, everything is highest priority. And, you know, our priority is your business customer. I believe that priorities need to be computed dynamically as a function of the value to cost ratio. And we do it with a spreadsheet, and that is engineering. Hope I made my point. If not, you can read about it in some of the books referenced.
Tom, question on that slide.
Right.
Based on value and cost, which I see, how does risk apply to this?
Okay. I have hidden the risk problem from you, but I'll tell you orally about it, and you'll find it in the books already referenced in depth. Okay. Now, here it is. When we estimate, say, 50% here, right? Mm-hmm. There's a little table, and it says plus or minus how much. And we think about it and say plus or minus 10%. In other words, it could be between 40 and 60. We're saying there's a risk that it's somewhere in there. It really is not exactly 50. Then we say, what is your evidence that it's 50 plus or minus 10? Give me the facts. Give me a case study, a measure, an academic paper. I don't care. And then give me the source of it so I can look it up and check it. We then assign a credibility level from 0 to 1.0, where 0 means you're just guessing, you have no evidence and no good sources. 1.0 means your sources are unimpeachable, solid, and this is going to happen. So we're dealing with the risk that you don't really know how good this architecture is based on facts. So long story short, behind these numbers in my real world, we have a variety of techniques for dealing with risk. You will find them in the earlier book, about 2 slides back, called SEA. Let's see, there it is. Systems Enterprise Architecture book. You'll find the detail on that. Okay. You'll also find it in the Competitive Engineering book. So that's the short answer, that we do handle risk, but I have left it out of this lecture. Except I got a good question on it. That's a good question. And I'm very, very risk conscious. And the engineering methods, that's the whole point of good engineering methods, is to handle risk. Okay. The biggest risk is you don't even try to estimate how good things are, and you don't even have clear quantified requirements to estimate them against. And there you have no idea of what you're doing. You're just doing it because you heard a rumor that Google or Intel used OKRs, so that must be the way to success. That kind of reasoning is so childish that people doing it should be removed from positions of power. Okay, so yeah, risk handling is very explicit in these methods, but it's a short lecture. It's not a 2-day course, so I put it in the books and I've given you the books. Question answered? I hope. So point 9, make it very short. I've always been very unhappy with yellow stickies, but I know a lot of people live and die with them. And for small systems, that's okay. That's great. Okay. It's when you get huge complex systems that yellow stickies gets silly, and it's time to go digital and put your information, at least in spreadsheets, digitally. Okay. And maybe we need to go further and put things in with, using Web3 solid standard semantic triples. And we're doing that at a place like graphmetrics.com, which I have a vested interest in. We're making extremely advanced digital systems. We've already made pretty advanced digital systems without the new web technologies, but we're now integrating them with the new web technology. So long story short, I believe that it's time to stop with yellow stickies and start putting our planning for our systems in digital form so it can be related. And all of the other illustrations I show you we have them in digital format. We do not use yellow. Point 10. Keep an eye on my watch. I've got about 10 minutes before I've got to shut up, and I've got about 7 slides. So I think I've got about 1 minute per slide here. People are interested when they are going for the large complex, they go to things like SAFe because they need a scaled agile method. And that's fine. I understand that the simpler agile methods don't scale and they need some help. I started thinking about SAFe at one point, and I said, I don't need SAFe. I don't like SAFe. And I knew from experience, and not least the experience of my clients like Intel, that my methods work on very small, simple systems. And they also work on huge, enormous, global systems. I just knew they did it. I didn't think much about it. And so I put it to my friend Eric Simmons at Intel. He's the one who's been teaching Intel for 20 years how to use my methods. And I said, Eric, what's going on here? And he said, Tom, your methods are not methods that scale. And I thought, oh dear, that's terrible. I thought they did. No, your methods are, in fact, scale free. That is, they simply work at any scale. They work, every large company has lots of small projects too. If you have to do small projects, it's a shame you have to go to the bureaucracy of SAFe to do it, maybe, okay, or have to have totally separate methods. So long story short, Intel has proven and documented, here is the whole paper on scale free, that the methods I'm talking about work on very small scales. That means one man and a dog for a week. and very large scales. That means the air traffic control system for Europe or something like that, which we in fact have worked on. Okay, so there's an interesting idea. Scale free is a possibility and is an alternative to safe. And by the way, it's free. The methods are essentially free. Anybody can adopt them. Here's a simple example of agile engineering on a small scale. Now, when I say small scale, it's not one man and a dog. It was, in fact, 16 developers who had a project that was in trouble with technical debt, to put it mildly. Like they'd hacked it together with spaghetti coding so fast that it was dangerous to change, and the user interface wasn't all that hot. And so they had a problem. They were just about to get out-competed by nimble new competitors. But they started using these methods. Make a long story short, there's the whole case study with all the detail. Here you see an impact estimation table used. And they very quickly brought up several of their qualities to such a high level that they put their international competitors out of business and bought them. Okay, a little Norwegian company. Okay, that's pretty good. That's small scale. Okay, and the whole case study is right there. Okay, so that's, in other words, even if you're only 16 people, you might be able to use these methods to successfully outcompete international competition. Number 12 out of 17. There is hope here. 7 minutes, 7 things to do. It is what I call my basic principles of agile engineering. Now, if I had much more time, I would, use 1 minute on each of these principles. Now, obviously, I, not surprisingly, run out of that. But if you'd like a summary of the basic ideas, here they are. You need to quantify your requirements. You need to estimate quantitatively how good your strategies are. You need to start doing things incrementally and measure and see how much value they deliver every week or every 2%. You need to contract for value delivery, not for work done. You need to work at the systems level, not the code level. Okay, so let that be a 1-page summary of my whole talk, what I'm into, what I mean by it. And by the way, if you'd like a whole book on value agile, here's a free copy. Here's a video. Here are the slides. What can I do for you? We've got to get something better than what's out there now. Okay. By the way, this has been out there for over 20 years in places like Intel and Confirm It. So we have 2 decades of successful use, at least, of these methods. So it's not like these are completely new, but they're new for you if you don't know how to do them. Okay. Number 13, there's a gang called Essence, which is, strangely enough, trying to collect everybody's method like Scrum is collected and put it in a database of all possible methods, and says, hey, pick your own method. Pick anything you like from various methods. Put together your own method. No license. It's all free. So I thought, that's a good idea. So I said, I will give you my method, my planning language. And so I wrote a whole book on it. Now, the book is organized. You see the different things. Here, by the way, risk management. Guy who asked the question on risk management might like to look at this. Book is free. But so it's designed so that you can pick any detail and pull it into your current methods and see how it works. You don't have to go totally Planguage or Guild or anything like that. You can pick one little thing that you need that tickles your fancy for free and try it out and see if it works for you. Okay, I got my five minute to shut up and invite questions alarm just now. Okay, anyway, so there's a way of, this will be integrated. They're working on it in the Essence world, but right now you can have the book and you can pick and choose anything you want. And it's another way of getting a view of what I'm talking about, the engineering here. For example, if you're interested in risk management, go to chapter 7. This one is really just emphasizing that free copy of the Stakeholder Engineering book. And have a little joke here. This is my books. Even if you find a book that has a price on it, like $5, I'll give it for free to any poor students and Ukrainians and I'll give it to the Turks after Sweden is a NATO member. My little joke for the day. I'm in Norway, in case you didn't notice. Here is the greatest agile practitioner on the planet, Elon Musk. And I started collecting his basic 5 ideas, which he just talked about at a walkabout at SpaceX. And they're brilliant, they're deep. I like this one. Your requirements you should assume are wrong, no matter how smart the guy is, like Elon Musk, who says them. And you need to try to make them less wrong. And the same with designs. So it's a constant skepticism towards the quantified requirements and designs. And then there's stuff here about deleting superfluous stuff, maybe too much. There's stuff about simplification, optimization. There's stuff about accelerating the cycle time. Musk can produce cars in Germany 3 times faster than Volkswagen can for some strange reason. And there's automation. Now, the other thing is, he says you must complete these processes in order, because Musk didn't. He went overboard automating the Model 3 too early and got into deep shit, because these things, he was automating the wrong things. Make a long story short. So this is really interesting 1-page summary. Now, these are the same methods I'm talking about. I think Musk just used his intelligent common sense to arrive at exactly what I've arrived at. I've got some pages here saying why, analyzing these in more depth that I obviously don't have time to go through. But if you'd like more depth analysis, and you'd even like a free copy of the book called Musk's Methods, should be in here somewhere. Let me know if you don't find it. And I have a free copy of Musk's Methods. There's Volkswagen being jealous. There's the automation and stuff like that. My car is the safest car in the world. I drive the Model 3, of course. Interesting, when you focus on safety as a value, you literally end up with the safest car in the world, and can't be bothered to brag about it. Either people are smart enough to find it, or they will die in their car. There should be a Musk Methods free. Okay, if you can't find Musk Methods here somewhere for free, I will send a free link on request. It's now about 100 pages of Elon Musk methods, and I think he is the greatest practitioner of Agile, as it should be, and the proof is in things like his cars, his spaceships, and his stock price. By the way, I invested beginning of January at $1.35. It's now at about $200, and I made a small fortune because Musk uses good methods. So if you're looking at anybody who has Agile methods, ask them if they're the richest person in the world yet, and say, if not, say, however strange this guy Musk is, he's strange, he obviously knows what he's doing in producing spaceships, cars, and software, which is half of the car, and probably half of the spaceship. So that was the Stakeholder Engineering book. Okay. I've become enamored with the idea of simplifying things. So just for fun, I wrote a whole book on it, and it's a work in progress. It's only halfway there, but you will find in the references a reference to the Musk Methods book. Okay, so going to my last 5 minutes. So I'm supposed to shut up pretty soon, and I will, but enjoy the beginning of my simple book. I've invented a simplification to beat the iron triangle called the Penta method. And I don't have time to tell you about it, but maybe you'd like to read about it if you'd like something much better than the iron triangle, which fails to bring in designs and values, and therefore is actually wrong. Okay, end of presentation. Questions, 5 minutes. Okay, and Linda, we got any questions we can?
I've got a lot of questions here now. People have had an opportunity to write some of them in. Robin had a statement that says, I agree with your points, but I fear the industry doesn't recognize them. My recollection is that the term software engineering didn't become common until long after your writings on it. And so far as I understand, it at this point in time, it's only meant for programming in the C language. That's just a comment. Do you have any comments on that, Tom? Hello, Tom?
Let's see. No.
I'm hearing you now. Tom?
Can you hear me now?
I can hear you now, Tom.
Okay, thanks. Okay, I am redefining what software engineering means to be real engineering, real systems engineering. That's the long and short.
Okay. Yeah. It needs to involve a whole lot more than coding. In fact, what I have heard is that coding should be about less than 20%, more like 10% of your life cycle activities if you're doing it right. That the focus needs to shift left to doing good requirements and design. That's my opinion.
You're right.
Charles asks, the current agile methods seem not to work, just ceremonial. What is really needed?
Number one, you need to define your requirements for critical success factors quantitatively. Okay, only then have you agreed and defined success and can then track your progress towards that success. And I'll simplify my answer there. People do not define their success factors. By the way, I have a little booklet I'll share with anybody called Success, which makes this point in detail. It's free, okay? So you need to define your top 10 critical factors quantitatively. Then based on that, you get agreement. These are our official top 10 quantified factors. And then you start your agile process moving towards those 10 objectives. And if you don't start with the quantification of your critical factors, nothing else counts, nothing else can be done. And unfortunately, things like Scrum, to take a simple example, have no such process at all. Okay? It's just about coding and things like that. So yeah, so long story short, start with clear definition of success and then use Agile to get there.
Okay, this one's for you, Tom. Pat McQuaid says, hi, Linda and Tom. Just wanted to thank Tom for getting through all of his slides. I know that's such a challenge for him.
Hi, Pat. Lovely to have you here. Yeah.
And Moss asks, oh, I'm sorry, go ahead.
No, go ahead.
Moss asks, in one slide, it showed verification is testing defined as verification, software or testware. Where does exploratory testing fall under engineering?
Okay, now, number one, many of the lectures you have, Linda, deal with testing in much more depth than I intend to do here. So many different forms of testing at many different levels. And I was specifically talking about one type, which was you put in an increment and you're not just testing for bugs, you are measuring what happened at that increment with regard to cost and values. That's the only type of testing I am discussing here. Now, there's a huge area of, number one, testing, which your other lectures and courses cover very well, Linda. And then there's quality control and quality assurance, much of which is not testing at all, such as my specification quality control method that I was at Intel. Look at that slide. So long story short, validation and verification is a huge area, and doing these engineering things that I'm talking about, quantifying and clarifying, enables us to test the right things, like am I reaching 99.98% availability, not do I have a bug? Wrong question. That's the short answer.
Yeah, and I will add to this, verification is all about making sure that the requirements as specified is met. Validation is all about, no matter what you wrote down in your spec, making sure that the intended use of the software has been met.
Good, I'll live with that.
And there's kind of two levels of thought here. If you look at the ISTQB, the International Software Testing Qualifications Board, it talks about testing as the broader activity, which includes static testing such as peer reviews and your analysis tools, all of those kinds of things that look at the product without executing it, and then dynamic testing where you're actually executing the product in unit testing, integration testing, system testing, and so on. The other view is, and they talk about verification and validation being two of the goals of the testing. It's two different mindsets of looking at what you're looking at as you're testing. The other mindset talks about verification and validation being the overriding thing, and you got dynamic verification and validation, which includes quote unquote testing, unit testing, system testing, acceptance testing, and then static V&V. So it's one of those, the industry doesn't even agree on the terminologies. So this is a hard question to answer, unfortunately, Moss, because even the major players in the industry are not looking at, is V&V the higher one or is testing the higher one?
Right. No, but as I said, your team covers this area very well, and I don't pretend to duplicate it or know better.
Okay, thank you. But my point is, Moss, what you have to do is define them consistently and use the terms consistently within your organization, because
that
there's
helps.
not that much agreement outside, in the industry in general. There's several ways of looking at it in the industry in general. And finally, we have a thank you very much for the great presentation from Monica. And that is the last of our comments and questions, Tom.
Okay, and remember, if you think about something afterwards and you email me, I'm very happy to answer you.
And one last slide. Here is Tom's, tom@gilb.com. Or you can go to just www.gilb.com for lots of downloads, et cetera, and he's got all kinds of references throughout his materials for additional personal study. Got one last thanks, Tom. A lot of good information today from Michael.
Thanks for inviting me. Thanks, Michael.
And with that, we will end the webinar for today. Thank you all very much for your kind attention. See you next week.
Bye.